get to the bottom of this, let us say, and so essentially I will try to argue that basically we live in a nonlinear world, and since we live in a nonlinear world which supports generation of self-organization, which supports generation of self-generation of complex structures, linear mathematics, linear physics on which quantum mechanics is based cannot by definition produce these things. So basically entanglement, as I will try to argue, is only a linear manifestation. I'm not using the word approximation. It's a linear manifestation of complex structures, and complex structures are based on chaos, which is entirely nonlinear, extreme nonlinearity. It is based on complexity, which is again evolution, it is self-organization, it is the emergence of properties which come on their own. Now, basically the point to remember is that none of these characteristics can come through linear mathematics. And therefore, let us say that this theory is basically anti-linear, if I may use that word. And why do I do that? Well, let us look at some of what our peers have to say. According to Stephen Hawking, in 2000, essentially he believes that this present century will be a century of complexity. Then we have a Nobel laureate, David Ross. He was one of the founders of string theory. Now, what does he say? What he has to say is that the present state of physics is like when people first discovered radioactivity. They had missed something very vital. What we are doing right now is that we are missing something equally vital. What it is, we have no idea. Finally, Lee Smolin, who is the most outspoken critic of string theory and is essentially one of the basic founders of the Perimeter Institute, whose basic job is to investigate these matters to its foundational aspect, says the last one in a book which I would encourage all of you to take the trouble to read, which says, "The Trouble with Physics, the Rise of String Theory and the Fall of a Science." Well, he in fact goes on, that is not given here, but he in fact goes on to suggest that the present crisis in physics, which he says is since 1975, nothing really has happened in physics. That is his summary, is because of string theory, because the best of brains have gone to string theory, and ultimately, well, that's it. So, basically, we are talking about a different paradigm, a different language, a different mathematics. And from this different mathematics will evolve a different physics and therefore a different interpretation of this physics. What is this different mathematics? It is anti-differential equation, because differential equations essentially lead to continuity. It leads to smooth problems, basically jumps and things and singularities. Some of the things which traditional physics will try to avoid as much as they can are always differential equations. The evolution of differential equations cannot take care of these things. But these are the things that chaos and complex structures basically depend on. So basically then, what is it that we need? Well, the basic point is that reductionism has possibly, well, I should not be misunderstood, but has possibly reached its end in according to Lee Smolin. It probably cannot lead to anything more. Just as classical physics reached its end at the turn of the last century, and quantum mechanics had to steer it around that. So probably what we need right now is not reductionism, but holism. And what is holism? Holism is the principle that parts of any whole cannot exist and be understood except in the relation to the whole. And this, by definition, this entirety of things evolving on their own, structures, life as we experience it. Why are we all here? Second law of thermodynamics would have suggested, and it in fact demands, that order should not exist. But then we are examples of order existing, very much so. So what happens? Has the second law been defeated? Has the second law been broken down in living systems, in open systems which interact with their environment? Well, the answer is no. And this theory of canonicity, or whatever you might call it, which stands is an acronym of chaos, nonlinearity, and complexity essentially tries to suggest how this is possible. Okay, I think I will skip all of this because this is a huge thing which I do not want to go through. But this essentially summarizes the reductionist versus holistic methodology. And as you can see from here, that in holism, what we look at is a synthesis, the last one, the synthesis as compared to the analysis. Analysis means you break it down, you reduce it to its parts, and then you study the parts, and then when you have studied the parts, as best as you could, put them together, you get the whole. That is not what happens. That is not what life is all about. All of us have approximately some 210 organs, but all of us are different. If it was not so, if there were no holism, if it was all reductionism, then all of us would have been identical. Okay, now again I can get rid of this. And I don't think that because we are going to ultimately spend a good part of our time on looking at the issues which are concerned us here in this symposium, in this conference, that of entanglement, through the eye of this holistic canonicity approach. So then, basically, what does it try to do? It deals with difference equations. Its basic structure is difference equation and not differential equation. What is the big difference does it make? It makes all the difference because difference equations iterate, it evolves. At a particular time, it evolves on what was the immediately prior to that. And this word prior I am using in the strict mathematical sense, following and preceding and all that sort of thing. So basically, unlike differential equations, if I give you the initial condition now, it will evolve according to that initial condition till whatever time you want it to evolve to without any interaction, basically without any interaction. Whereas this essentially takes into account all the interaction that appears of the system and its environment, and thereby basically is able to lead to emergence of new properties, which is what this entire thing is about. So again, I think I will skip all this. Now, essentially, this theory is not metric space based; it is topological based. Now, what is topology here? Topology here essentially in terms of topologies, which are basically given in the properties T1, T2, T3. And what we are basically interested in is the idea of convergence, because evolution is an idea of convergence. The things are evolving, and ultimately they are showing up in a certain form, which is a result of evolution, which is a result of convergence to a certain well-defined structure. Now, in all this, you have to realize that something that has not been mentioned so far, at least I have not heard it in the lectures that we have been hearing, that is the second law of thermodynamics. It is the supreme law, as far as some people would have us believe. In fact, Sir Arthur Eddington had famously said that, well, if you have revised something, if your theory says that, well, the Maxwell's equations are wrong, then, well, he says the experimentalists do blunder sometimes. So that could very well be. But then if somebody says that the second law of thermodynamics is wrong, then the only thing that Sir Arthur Eddington could advise is that he will simply disappear in oblivion. Nothing will happen to you. Well, without getting into the semantics of all that, what it essentially implies is that we have to take into account, since we are talking of evolution, since we are talking about how things will ultimately emerge in time, we have to take into account the serious fact of the second law of thermodynamics. Now, the second law of thermodynamics tells us that ultimately everything becomes degraded, dissipated. Nothing appears as order. Order gets automatically degraded, but the dissipated state never on its own gets ordered. So this is the fundamental difference between order and disorder, between living structures which are examples of order, and the dead state of what the second law of thermodynamics would would have us believe. The question is, how does this happen? Why is there order in the world? Now, this is part of the complex structure, and this essentially, this is very important, it's the multifunctional extension of function spaces. Essentially, all the physics that we do is basically in function spaces. We take care that multiplicities, we take care that we don't have a sine curve standing on its edge like this. We don't have that. I mean, that sort of things essentially is not very well dealt with in physics and in mathematics. We always want specific well-ordered theorems. We always want specific uniqueness results and so on. Now, multifunctions mean that a point in the input can lead to many outputs. Now, this essentially has the implication, as we shall see, that basically what we're talking about is, in a sense, quantum mechanical, because quantum mechanics has this wonderful property of a wave. It's not localized. Heisenberg's principle tells you that if you want to localize it, its momentum, its energy will get delocalized. So essentially, spreading out, being omnipresent, is one of the basic properties of quantum mechanical thing, and entanglement is a manifestation of that. Now, when we start with multifunctions, it says that there can be many outputs of a given input. We are already getting into that sort of argument, but then there is a very important and subtle difference, a difference which is the basic difference, which will ultimately lead to the basic difference between what I'm saying and the entanglements as we have been hearing from the morning. And the difference is that this is nonlinear. So basically, this is strong nonlinearity. Therefore, basically, superposition principles do not work here. And once the superposition principles do not work here, then I can have as many solutions, etc., and basically choose from any one of them by something known as the axiom of choice in mathematics, and get results which will not run into the measurement problem of quantum mechanics. The measurement problem of quantum mechanics is a very fundamental problem, and that leads to all sorts of interpretational problems with quantum mechanics. But then basically, if we want to work with nonlinear systems, strongly nonlinear systems, which essentially are multifunctional, that means it does lead to a basket of possibilities. All that we have to do, measurement, what is measurement in that case? All that we have to do is simply to pick up one of them. And how do I pick it up? Axiom of choice. Whether you believe, if you believe in axiom of choice, use it. If you don't believe in axiom of choice, well, you don't really have much, you cannot do much about it. Okay, so this multifunctional and this space, the multifunctional space, has been shown to be essentially an extension of functional space. So basically then, what we get into is, let me quickly skip all this and get into this concept of a negative world. Now, what is this negative world? The negative world is, think of it, without going into the details, think of it as the negative reals and the positive reals. The negative reals are the negative numbers. Now, if the negative reals did not exist, then essentially the real line would be incomplete. Mathematically, it would be incomplete. And you would only increase. You would go from 4 to 5, 5 to 6, but you would never be able to come back to 4 because the negative numbers do not exist. So basically, the negative world is a product of this sort of an argument that I can define some non-real quantity, this. Actually, I have defined a space W which for every W in the real W, let us call this the real numbers, I define something whose union gives me essentially 0, the empty set. Now, this never happens in the real case. There's nothing which I cannot have a set and take one element from that set and take another element from another set, take the union and make it phi, the empty set. That doesn't happen. But then, just like the reals, I cannot have 4 plus 2 less than either 4 or 2 unless I take 2 from the negative. So similarly, I define a negative space which is denoted by these script letters and define the union of the real and the non-real as this. So this is a perfectly valid assumption, a definition. Now, once we accept this definition, then various mathematical techniques can lead to what we call the exclusion space, the exclusion topology, the exclusion space, which basically is a mechanism which is essentially topological correspondence of, let us say, the real lines. And the job of this is simply to monitor, to inhibit the growth that would otherwise be there in the without the negative part. So what is the use of all this? The use of all this is as follows, that second law of thermodynamics and the question of how the living systems appear, how they apparently defy the mandate of the second law. This is from the fact that I can always, this exclusion topology and the negative world essentially can be extended and projective limits, etc. But then when I translate all these ideas to the thermodynamics, these two now, if I want to look at it from what we understand materially, essentially becomes a coupling of a pump and an engine. The engine is the stuff which degrades. It is the dissipation, expansion. What we need to have order is a component of compression. And that compression is through a pump. How does this happen? This is where complex structures come in. This is automatically generated by the system. Nobody does it. It simply happens on its own. That is where the complex structures come in. That is where emergence comes in. Emergence, it is not programmed. It happens on its own. So this entire thing essentially can be put in a complete thermodynamic language, work that you get, the maximum work that you get. W is the actual work on a non-reversible cycle that you can possibly get, and the assumption is that this W is automatically fed back into a loop which generates P. This is essentially positive and negative feedback, nothing more, nothing less. But we are now trying to adapt all this to a particular holistic character of how it happens, and suggesting that this is how the open thermodynamic systems, in fact, a macroscopic property which has to be explained, which has to, because it is one of the intensive properties, and essentially you have to basically figure out what is the role of temperature in all this. And if I look into all those properties and we go through the details of all those properties, then what we shall find, which is quite different from the traditional things that we do, is that temperature, there can be two temperatures. One is this graph that you see here, and the other is the dotted one that you see here. And this dotted is essentially in the negative temperature regime. These are absolute temperatures. This is the Kelvin temperature. And therefore, having negative temperatures is simply not the rule of the game. You don't have negative temperatures. You don't even have zero temperatures. You cannot get even close to it. And that is where the Bose-Einstein condensation, etc., comes in. So basically, this theory leads to two temperatures. One is this is our real world. This is what happens, and generally it's the negative world. And now what is the complex structure? The complex structure is that these two act together. I mean, once they have been generated on their own, they act together and they produce whatever we see. Now, what does all this have to do with quantum mechanics? Well, the following. What it has to do with quantum mechanics is that basically this part that we see here, let us not go into the details, is essentially what is chaos, what we call chaos. And this negative temperature zone is not there. I mean, it doesn't have a physical counterpart in the real world, so we will not try to assign any meaning to this, but these two together make up the negative world, the anti-world, as you may call it. And basically, what happens is that this negative world, so basically in these two temperatures, I can now take Tc as a variable, keep TH constant, if I keep TH constant, I mean, there are reasons why I'm saying that TC is a variable and TH is a constant. TH is the higher temperature. Think of the higher temperature and the lower temperature and an engine running between the two. Essentially, this is the same sort of thing. But then, basically, now I hold the TH constant, and there are reasons why I'm holding TH constant, and allowing TC to change. If TC changes, that's the lower temperature, so it can go how low? At the most 0, because this is the real temperature. This is not the negative temperature. And how high can it go? It can go, TC can be TH. Why not? Let it go TH and see what happens to the equations. And let it go beyond, in excess of TH, be larger than TH. Then what will happen if you go through the exercise properly, then what you will find, they join together. And they form one entire, and this completely forms the negative world, and the real world TH goes from 0 to infinity. Now, obviously, they have a boundary. T equal to 0 is the boundary. What happens at that boundary? Well, we have arguments to show that that boundary basically corresponds to the quantum mechanical description as we understand it. And if we do that, then other concepts like the black hole, etc., seem to follow in a natural way without, and most of the paradoxes of quantum mechanics, the interpretational paradoxes of quantum mechanics, for example, the measurement problem which I mentioned at the beginning of the talk, this seem to get resolved. Now, the only thing that I can say is that this paper has essentially gone through a very rigorous sort of scanning by the journal Foundations of Physics, and they were prepared to publish it with certain changes which I did not agree to. So basically, probably what I'm saying is not really meaningless. Okay, now, what is the distinguishing feature of quantum mechanics as differentiated from classical? Well, this is what we have been talking about since the morning, superposition principle, Hilbert space. Classical mechanics does not require a Hilbert space for its foundation. Quantum mechanics does. Every ray is a state, and every state is a ray. This is a very strong statement which quantum mechanics makes, and essentially, I believe that most of the problems arise from that. Because if I do take as an assumption or as a hypothesis that the world is nonlinear and not linear, the superposition is no longer a matter of right. We do have a multifunction, therefore there are many, many possible choices, and all that we have to do is to apply the axiom of choice, pick up under the given initial conditions, define a choice function. The choice function, definition of the choice function will reflect your initial conditions. So I define the choice function, which reflects my initial conditions, and I pick up according to that choice function from that basket that the multifunction provides me, and that is my experimental result. So basically then, if I go through this approach, then you will find that most of the quantum mechanical paradoxes seem not to exist. Now, I'm sure that if these are examined more carefully by people more qualified than I am, things will change. I expect them to change. But basically, I suppose that there is good ground to sort of take this alternative way of looking at things and at least try to look at it seriously. Okay, now, yeah. Now, why do I say all this? Because entanglement depends on tensor products. This is the most fundamental thing. And what is a tensor product? Tensor product is when I'm trying to build up a composite from units. So basically, we are talking of here since the morning of spin-up and spin-down systems. So essentially what we have, one is up, one is down. Again, one is positive, one is negative. R plus, R minus. Negative world, real world. So essentially, I can interpret it that way. And if I look at, okay, I'll come back to that later on. But then what is most important here is in the tensor product is that if I have 2 qubits and I want them to interact, each one of these qubits has dimension 2, so it will be 2 not into 2, which is equal to 4, but 2 to the power of 2, that is equal to 4. Now, if I have n qubits and interacting, then it is 2 to the power of n. And this is what gives the quantum computers its magical property. That now, classically, we would have, if I do classical statistical mechanics, then with n bits, I can have only each in the up and down position, I can have 2 multiplied by n, not 2 to the power n. And this makes a huge amount of difference if n is suitably large. And this is where the property of quantum computing essentially lies. Because after all, you're writing down the tensor product of 2 matrices, a linear construct, as another matrix of power n squared when we are talking of 2. I mean, n such matrices being put together, spin down. Now, this is the qubit. So essentially now, why is this a qubit and not a classical bit, 2 classical bits? Well, simply because if I take an output here, I do always get 2 values. This is the multifunction. So essentially, one output gives rise to more than one input. That is basically the property that we are trying to use here. And then, since this is a function, then what we do, we take it as equation fx is equal to lambda x on 1 minus x and iterate. What does iteration mean? Evolution in time. But this is an evolution in time, not as a differential equation. But then if this is f1, or if this is f, then the next one is I replace this x by the previous f. Then in the next time evolution, I replace this x by fx. So that becomes f3x. So basically then, at each instant of time, it is depending on immediate predecessor. This is what brings about the fundamental change in the properties. And this fundamental change is shown here in these diagrams. Depending on the value of lambda, this qubit, let me use that language, if iterated to infinite time, that means allowed to evolve infinitely, will give rise to this, the horizontal, I mean, this structure that you see here. This structure that you see here. This complete structure, 1, 2, 3, 4, and this entire thing that you see here. And this structure if lambda is sufficiently large, and this structure if lambda is different. And this is essentially what happens in this sort of game. This is the equivalent of the entangled states, okay? Because now in this particular case, if I look at this as the 2-qubit entangled state, then what we have is that the ultimate object here, or the ultimate object there, basically is an entity in itself. And this is a complex structure, this is a complex evolved structure. You cannot, by definition, remove any one of the constituents of that complex structure. And what are those constituents? The constituents here are these points which are marked with solid dots. These are the unstable points, unstable fixed points of the entire process of iteration. These correspond to this. You see, this is I can see here 1, 2, 3, and 4, a 4-tiered structure. Here I can see 1 and 2 tiered structure. So this is 2 to the power 1. This is 2 to the power 2. This is essentially 2 to the power infinity. What happened? This is full chaos. Oh no, yeah, this is full chaos. This is at 3.57. You get into the region of full chaos. Now. The basic point is that this is my macro structure, and these 4 unstable fixed points, these 2 unstable fixed points, they are the micro structure. So essentially now I'm trying to correlate the Boltzmann entropy relation, S is equal to K log W. So what is in this particular case, what is W? What is the number of microstates? There are 4, 1, 2, 3, 4. And what is the macrostate? This entire structure that you see here. I cannot remove any one of these fixed points without the entire system collapsing, without the entire complex structure which has been developed collapsing. Now, witness this to partial tracing in the theory of entanglement. You do get significant information, in fact, all the information, by partially tracing over one of the variables. So basically, and that is a valid way of doing things. But now here in this particular case, you just cannot do that, because if you try to remove any one of these particles, then the entire structure is going to collapse. complex structures do not allow that freedom. Obviously, that is also up. So that is how the entire thing goes. Now, decomposition. And the Smith decomposition guarantees that such a entangled state can be in which the entanglement is expressed. So in our basic states. And from this, we get into the mixed states, from which we are getting the individual S is one qubit, E is the other. So we put them together and get this SE. But then by partially tracing, we recover each one of these, each one of them separately. And one important part is that this index R remains the same in both cases. So basically, this is forbidden by what I have just described. So in the way that we want to argue, complex non-locality is a much stronger form of entanglement than quantum non-locality. Complex holism, let me put it that way. What we have just described is complex holism. Complex holism is a much stronger form of entanglement than quantum non-locality. And this can have serious repercussions on quantum computing as we understand it. Because decoherence is, I think, please correct me if I'm wrong, the experts in this field, decoherence, I think, is one of the most troubling factors of quantum computing. Because with decoherence, the entanglement gets destroyed, and thereby the power of 2 to the power n gets destroyed. So essentially, but such a thing, as I said, since it cannot happen here, should not be a problem if this is what is happening as compared to the...
Professor Sengupta, sorry to interfere, but I think for the benefit of the students, at least, it would be nice if you could kindly tell what, like, you know, in case of quantum mechanics, we typically solve Schrodinger's equation or the nonlinear form of the Schrodinger equation. Or we go and solve linear algebra in terms of doing density matrix evolutions, which are Liouville forms of the differential equations. What is the exact mathematical form or the model that you are solving? If you could kindly tell that to the students, it will be really helpful.
What is the mathematical form of the model? I do not think we are considering any model here. This is a very general prescription. So we are not considering any model whatsoever. All that we are trying to say is that if an open thermodynamic system has to exist thermodynamically, that means in defiance of what the second law tries to tell us, then this is how it happens. And these structures that I have shown, which I was trying to get to, these structures that we have shown, they are this engine and the pump, this the negative world and the positive world. They get together and produce this thing. Okay, now to answer your question, maybe I can... Okay, I was trying to get to this. Now you see this entire, these two that I said is is responsible for the negative world, and this is the positive, the world that we are in. These can ultimately be used very judiciously. In fact, the example 4 of the paper that you mentioned, to understand ferromagnetic and paramagnetic. And basically, let me get to that example 4 and answer your question somewhat. This is it. Okay, now, you see, this is the picture that we have here is essentially obtained by considering the we consider a two-state paramagnet, that means up and down paramagnet, of n elementary up-down magnets, dipoles, in a magnetic field B in the plus Z direction. Then these expressions are well known. This E, for example, is the energy. Now, once this energy is known, then I can use the standard equations for thermodynamics and basically obtain this graph of the specific heat, this graph of the temperature, which has a discontinuity at energy equal to 0. Negative energies are the bound states, this positive energy are the non-bound states, and I can have expression, a diagram for the entropy also. Now the entropy plays a very significant role. In fact, what happens is that if I look into the ferromagnet transition, then this is supposed to happen at the critical temperature by a second order phase transition, basically. Now, how does this happen in this particular case? I'm not very clear about that. But basically, I do think that such a thing is taking place. I'm trying to work on it right now as to how the second order phase transition comes in. But a very important role is played by the T equal to 0 temperature. That's a very, very important thing. In fact, the T equal to 0 temperature, it is non-accessible because it is a boundary between the real world and the negative world. And this is the place where, which is the domain of quantum mechanics, because quantum mechanics, as I have tried to say somewhere in this paper, is a linear representation of a fully chaotic state. So, I mean, other than that, I think it is very difficult for me now to explain to you if we do not have time to actually go through the details of these discussions. Okay, I think I will stop here, and if you have any further questions, if you want me to elucidate something, that will be my...
The paper is now open for discussion on the floor.
You see, this particular figure, if you open up any book on chaos theory, you will find this figure, without all this, you will find it in any book of chaos theory. And this is supposed to be the period doubling bifurcations. So now here, I can, in my paradigm, I can look at this as a spin up, spin back down. Then this is, from this, those black dots that I had shown on the diagram. These are those points. So again, there is one spin up, one spin down, one spin up, one spin down. And ultimately, when you get to this parameter lambda, remember I showed you a lot of diagrams with different lambda values. So at this lambda star, it gets into the chaotic region. Now that is what you will find in any book. Now these few lines here are basically according to what we are talking about. And this T, alpha, iota, this iota is the reversibility constant which I had shown, and this T is the temperature. So basically what happens, because through equivalence classes, which is very important here, equivalence classes generated by the multifunctional mappings. Basically what happens is that the temperature T equal to plus infinity and T equal to minus infinity get mapped onto each other. You can think of putting them round, okay? So plus infinity or plus or minus, putting them round and making them meet. So that is what happens. T equal to plus infinity equal to minus infinity. That is how this T equal to plus minus infinity appears. Now this thing that you see here is essentially this entire region. What I have stated is that this region is the quantum mechanical region. Now why do I say that? Because I do have something, power laws, power laws, the Zipf's law, and these are very, very standard things that one talks about in all these things. You try to see whether a particular law, a particular theory which you are describing can be described by something like x to the power n. N is not an integer, that is the fractal dimension and so on and so forth. So if that is possible, in this case we show that that is indeed possible, then this thing in this region, what happens is that that n, let us say, starts increasing from 0 to 1 here at this point where it becomes entirely chaotic, and then as it crosses, it drops to 0. There's a sudden jump from 0, from 1, which it gets here to 0 just as it crosses. Lambda star minus the parameter chi, that is the end that I was talking about, is 1 at lambda star plus the value of chi is 0. Now, whenever there is such a jump in some physical parameter, that signals the birth of some new unexpected characteristic. And what happens is that in this entire region of chaotic region, which are these lines, these are windows, let us not get into the details of that. In this entire region, the value of chi remains 0, it does not change. And then as it goes beyond 4, it suddenly becomes 1 again. So now by equivalence arguments, I can say that this 0 entirely is equivalent to these zeros here. So now when something, you see what happened is, if I again get back, fx is equal to x to the power chi, let us suppose. And then as the chi value is increasing, then it is, if chi is equal to 1, it is linear. If chi is less than 1 but more than 0, then it is nonlinear. As it is approaching 0, then it is the most nonlinear. Okay, it gets into a multifunction. So basically, if this is 0, then, and it is chaos, then it means that basically fx is equal to x, linear. So that is one of the reasons why we say that quantum mechanics is a linear representation of the fully chaotic state, because this parameter value of chi, which represents the power to which you must effectively represent the entire system as a complex structure, becomes 0 in that region. And because it is multifunctional, because in this particular case it is, well, I will not get back to that. In this region, if I look at those maps, then it will, you think of sine kx as k goes to infinity. What happens? You get infinite number of lines spaced together. So that is what happens in this particular case, as we cross lambda equal to lambda star. So it is infinitely multifunctional. So it is, I mean, quantum mechanically, it is almost like a wave, let us say. But then it is not a wave because it's not a solution of a second order equation. But basically it has a power which is 0, which is linear, effectively linear, and then it is spreading everywhere. Because I take one point in sine kx going to infinity on the y-axis, I get infinite number of points. So this is how we conclude that quantum mechanics is an effective representation, not an approximation, I again repeat, of the fully chaotic state.